Hey everyone, let's talk about signals. They're literally everywhere, right? From the Wi-Fi floating through the air to the music in your headphones, our entire modern world runs on them. And yeah, they can seem incredibly complex, but what if I told you they're all built from just a handful of surprisingly simple universal pieces? That's what we're going to break down. So that's the big question, isn't it? How do we even begin to make sense of all this chaos? I mean, if you were to look at the raw signal for a video you're streaming, it would just look like a total mess, a jumbled up, chaotic waveform. Where in the world do you even start with something like that?
Well, the answer is actually brilliantly simple, and it's an idea we all learned as kids. You break it down. Think about a complex signal like it's an intricate Lego model. From far away, it might look super daunting, but up close, it's just a bunch of simple, standard bricks. And once you understand those basic bricks, you can understand the entire structure. It's the exact same idea with signals.
So let's meet these signal Legos. We're going to dive into the three main families of them. Once you get a handle on these, you'll have the basic toolkit to see how pretty much any signal you can imagine is constructed. Okay, first up we have the singularity functions. Now these aren't your standard 2x4 bricks. No, think of these as the specialty pieces in your Lego kit. You know, the weird single-purpose ones. They are perfect for modeling unique, instantaneous moments, like the exact instant you flip a switch. And the most extreme specialty piece of them all is the unit impulse. This thing is, well, it's kind of mind-bending. It's a signal that is zero, absolutely everywhere, except for one single, infinitesimally brief moment in time. And at that one moment, its height shoots up to infinity. But, and this is the really crucial part, the total area under that infinite spike is exactly 1. It's the perfect mathematical way to describe a sudden, sharp jolt, like a single loud clap in a totally silent room. Next is the unit step, which is way more intuitive, thankfully. It's a signal that's just sitting at 0, and then at a specific moment, it instantly jumps up to 1 and just stays there forever. It's the perfect model for anything that turns on and then remains on, like flipping a light switch. Simple as that. And the third member of this family is the unit ramp. As the name suggests, it's just at 0 until a certain point, and then it starts increasing at a perfectly steady, linear rate. A great way to picture this is smoothly pressing down on a car's accelerator and just holding it in that exact same spot. Now, what's so cool is that these three functions aren't just a random collection. They're all directly related through a mathematical process called integration. So if you integrate that instantaneous jolt of the impulse, you get the switch flip of the unit step. Then, if you integrate the unit step, you get the steady increase of the unit ramp. They form this really clean, elegant mathematical chain. All right, on to our second family of signals. If the last group was the specialty pieces, think of these as the smooth, wavy foundational bricks that you see everywhere in nature. They're fantastic for modeling things that oscillate, grow, or decay over time. Real exponentials are just the fundamental shapes of change. If something is growing steadily, like a population, or decaying over time, like a radioactive element, it's going to follow one of these smooth, continuous curves. Things get really, really powerful with complex exponentials. And hey, don't let the word complex scare you. The core idea is what's amazing. This single function brilliantly combines two behaviors at once. It captures both a wavy oscillation and an exponential decay or growth, all in one package. This is absolutely essential for modeling things like a sound wave that's fading away. And of course, we have sinusoids, your classic sine and cosine waves. These represent the purest form of oscillation you can get. Think of a perfect musical note or the alternating current in your wall socket. Any sinusoid can be completely described by just three things: its height, which is its amplitude, its speed, which is its frequency, and its starting point, or phase. Okay, our third and final family, pulse functions. So while the singularity functions handled those instantaneous blips, these guys are all about events that are on for a specific limited time before turning off again. Think of them like time switches. The simplest one is the rectangular pulse. It's off, then it jumps to on for a set amount of time, then it jumps right back to off. This is the fundamental shape of a digital bit, the 1 in binary code. It can also be used as a kind of mathematical window to isolate and look at just a specific piece of another signal. The triangular pulse is, well, exactly what it sounds like. It ramps up to a peak and then ramps linearly back down to 0. It also has a pretty neat origin. It's the exact shape you get when you mathematically blend two rectangular pulses together in a process called convolution. And finally, we have the sync function. Now, it looks a bit strange, I'll give you that, with its big central peak and those decaying ripples. But this is one of the most important signals in the entire digital world. Why? Because the sync function is the perfect mathematical tool for taking a bunch of digital samples and flawlessly recreating the original smooth analog signal. It is the magic behind high-fidelity digital audio and video. So, we have our Lego bricks. Now, how do we actually use them and describe what we've built? Well, we can do that with just a few simple operations and by analyzing their core characteristics. We can manipulate these building blocks in 4 basic ways. We can scale their amplitude, that's just like turning the volume up or down. We can shift them in time, which is just delaying them. We can scale them in time, which either compresses them or stretches them out. And we can reverse them, just like playing a recording backward. All right, now for one of the most powerful and, frankly, coolest ideas in all of signal processing, symmetry. It turns out that any signal, no matter how complex or lopsided it looks, can be broken down into the sum of 2 simpler components. A perfectly symmetric part, called the even component, and a perfectly anti-symmetric part, called the odd component. Let me show you how this works. We start with our original signal here in blue. It's a mix of different waves, so it's not perfectly symmetric or anything. The orange line you see is just its time-reversed reflection, a perfect mirror image of itself. And here's the clever part. Just by adding and subtracting the original signal and its reflection, we can perfectly isolate its hidden components. We're left with a purely even part, which here is a cosine wave, and a purely odd part, a sine wave. And here is the final proof. When you simply add that even component and that odd component back together, you perfectly reconstruct the original signal we started with. We've successfully decomposed it into its fundamental symmetric parts. How cool is that? So we've met the building blocks and we've seen how to use them. But why does this whole toolkit actually matter in the real world? Well, ultimately, this approach makes incredibly complex problems manageable. Breaking signals down like this simplifies the math a lot. For something super important like Fourier analysis, using that symmetry trick can literally cut the computation needed in half. It reveals hidden patterns in physical systems, but most importantly, it gives engineers a universal toolkit to build, model, and analyze any signal they can possibly imagine. And this leaves us with a final thought. If every single signal, every sound, every image, every piece of data flying through the air is just a unique combination of these simple ingredients, it really makes you wonder, what new signals, new technologies, and new ways of communicating are we going to build next?